Thank you very much, Reverend Liz, for the invitation. And always nice to be talking in Miami. So this goes, you know. Okay. So the goal of this talk is to explain some aspects of the superconformal field theories of class S, and how a mathematical translation ends up involving families of Hitchin systems over moduli spaces and the study of the singularities of the spectral covers. And this is joint work with Ashwin Subramanian at Rutgers and Jack Bisler in Texas. So four-dimensional superconformal field theories have been a subject of study for many years. Recently, a class of such theories that admitted geometric construction from 6 dimensions have received attention. This includes several familiar theories with ultraviolet Lagrangians and more mysterious theories for which there is no known Lagrangian description. In the realization from 6 dimensions, the Hitchin system plays an important role. Specifically, the Coulomb branch associated to the four-dimensional theory can be described as the base of Hitchin system, associated to some simply Lee algebra J and ultraviolet curve C in the end. So you have a curve C with genus G and marked points, and put some algebra on it. Don't ask me why it's called J and not G, physics convention. The choice of the Lie algebra parameterizes the possible 6-dimensional theories, and the choice of the curve determines the compactification. And the effect of putting the punctures in just makes the Higgs fields be allowed to be neuromorphic. I'll review that in a moment. So a possible reason that this is in this conference is because of something called 3D mirror symmetry. So three-dimensional n equals 4 theories have a moduli space consisting of 2 branches, Higgs branch and Coulomb branch. And 3D mirror symmetry is supposed to exchange them, roughly. So Nakajima in 2015 wrote a paper where he initiates a mathematical theory of these things, and that was greatly elaborated by Braverman and Fingerberg and Nakajima, a series of follow-up papers. I can say a little bit more about 3D mirror symmetry, but the truth is I don't have anything to say about it. So let me just leave that as a black box and move on. So here's what the physics tells us. We'll consider what they call tame defects, which basically means that the divisor we mark on the Riemann surface consists of distinct points, where the Higgs field in the Hitchin system has a simple pole at the punctures. In order to obtain superconformal field theories using tame defects, you need the residue to be a nilpotent element in the algebra. And at some point, they start looking at massive deformations. The eigenvalues become the masses. So the massless case is the one that they're looking at. What really matters is just the J conjugacy class to which the element A belong, or residue. So it's helpful to label the Hitchin boundary condition by the nilpotent orbit, O sub A or O sub H. Does this work? Yeah, O sub A or O sub H. There are additional complications for groups other than SLN, which I'll describe in a second. But basically, you need to specify some additional discrete data. So in a word, it's known that if you take the centralizer of an nilpotent orbit, or of an element in an nilpotent orbit, it has the centralizer has a finite group of components that might not be trivial. In type A, and it's always trivial. In other types, it's not, and then you need to introduce additional discrete data to take care of, to account for those possible extra components. So this is one of several reasons that in the current work we focus just on SLN. Okay. So a crucial feature of this geometric organization from 6 dimensions is that you see what the moduli space is. The moduli space of the theories is the moduli space of the Riemann surfaces. And if you look more carefully, it's the compactification, the Deligne-Mumford compactification of the moduli space of punctured Riemann surfaces. When you restrict to a co-dimension 1 boundary condition, boundary stratum of MJ bar, the physicists see a weakly coupled gauge group with an associated gauge coupling related to the plumbing fixture. So, and it's basically the distance from the boundary, or the width of the generating Riemann surface. When you restrict to co-dimension K boundary stratum, you get K simple factors in the gauge group that all become weak. So I guess you can go all the way to the 0-dimensional isolated boundary strata. So those involve 3G minus 3 plus n simple factors, which correspond to the nodes of Pan's decomposition of the curve. And you have 2G minus 2 plus n isolated superconformal field theories that you're dividing. So you're roughly taking the product of 2G minus 2 plus n of these isolated field theories that have no moduli, because we've gone to 0 dimensions, and you divide by a group which is the product of that many simple factors. In the best circumstances, the group that you divide by is just J itself, or rather usually the adjoint group corresponding to the algebra J. However, there are cases where what you get is a proper subgroup H of J. So this often corresponds to somewhat surprising physical phenomenon that you can have a superconformal field theory with group J, which is S-dual to a superconformal field theory with a smaller gauge group, but coupled to non-Lagrangian matter. So this is where the non-Lagrangian stuff comes in. The first such example was due to Argyris and Seiberg, and this was later given a class S interpretation in a deep series of works by Gayotto. And my collaborator, Jacques Dissler, also wrote a series of papers. The key word there is tinker toys. He has a way of building these theories from elementary building bricks that he calls tinker toys. They roughly correspond to this pairs of Pan. Yeah.
It's true that this MJ bar really model space, so it's logarithmic structures, it's a deformation theory, it's not really what you see. You see that in general, my feeling is if you go to these boundary points, you get something like analog of mixed code structures. So kind of,
I'm going to talk about this in a minute.
No, it may be, as I said, it parameterized conformal field theory, but it's not really model space. Because it's cheap.
I'm not sure. This is the received wisdom from the physicists. I can only quote them. The theory you get, or a big chunk of it, turns out to be independent of the point where you are. So in that sense, it lives on a whole punctured neighborhood of the boundary, and therefore it's reasonable to expect it to actually extend across the boundary. But that's what they tell me. We show that the appearance of these smaller groups as the weakly coupled gauge groups can be understood using the Hitchin system on nodal curves. So that's going to be the main mathematical content of the talk. With this, one has a clear, or at least clearer, geometric picture of how the smaller gauge groups arise. Classification of interesting nodes and physically interesting Hitchin systems for a fixed J amounts to classification of the possible weakly coupled gauge groups that can appear. And we do this subject to some physics reasonability constraints. And conversely, the Tinkertoy classification gives you a bunch of examples, and then you can realize them using the Hitchin systems. So one concept that keeps appearing in this story is a trichotomy, which we do to Gayotto and Witten, and then in a slightly more relevant setup by Gayotto and Razamat, I believe it was. Anyway, they take the theories and they call some of them bad, some of them ugly, and the remaining ones are good. And then you can wrestle with you in the back. So, I didn't write this up. They describe it in terms of the Higgs branch of the theories. So they classify the theories into good, bad, and ugly depending on properties of the Higgs branch moduli. What we're going to do is we're going to translate it into properties of the Coulomb branch, which is basically the base of the Hitchin system. So, in case you are not familiar with the Hitchin system, it's a global version of the quotient map from the algebra to its Cartan or to the Weilbruch. So in the case of SLN, it's just a map that sends a matrix to its spectrum. So T is a Cartan, the algebra G, it's group G, W is a Weilbruch. So as I said, it's just the spectrum. Given a curve in the group and a line bundle L on the curve, the total space of the Hitchin system is the space of Higgs bundles. So it's the moduli space of L value G Higgs bundles on the curve C. For G plus GLN, this just means pairs V phi, where V is a rank in vector bundle, and phi is an L valued endomorphism of V, called the Higgs field. For general G, you replace the vector bundle by a principal G bundle and phi by an adjoint section. So again, there are different versions of this. You can have a stack, you can have a space, depending on which kind of portion you want to form. The base is a vector space. It's a space of sections of some slightly crazy thing. You take the line bundle, and you tensor it with T, and then you notice that the Weilbruch acts trivially with the line bundle. It's just the reflection representation of the Cartan. So this thing is a bundle over the curve C, and you take its global section, that's the base. There's a more explicit way of writing it in terms of invariant differentials. So a point on the base determines the W Galois cover, called the camera cover, C tending to C, which is just the inverse image. So you have a map from this thing without the W quotient to the thing with a quotient. If you have a point here, it's a section. Its inverse image here is a multi-section, like it's a W Galois cover. The choice of representation row of the group G maps the camera cover to what's called the speckle cover. So C tilde depending on row, which sits in the total space of the line bundle L, and parameterizing the spectra of the vector space of the morphism row of phi, all the points of the curve. When row is faithful, the data is equivalent, so you can work with spectra or camera without any loss. So explicitly, you can write down the basis global sections of those powers of L, where R, the number of summands, is the rank of the algebra, or the dimension of the Cartan, and the DIs, the powers that appear here, are the degrees of the G-invariant polynomials. So for GLN, those are just 1 through n. For SLN, they're going to be 2 through n. For the orthogonal group, it's 2, 4, 6, 8, and so on, plus, instead of 2n, you have half of that for the Pfaffian, and so on. Quotient map applied to the Higgs field phi determines the family parameter by C over L valued points of T and W, and this is the Hitchin. So the Hitchin map H from Higgs to B takes a bundle of the Higgs field and sends it to the family of points of T and W intersection. So Hitchin considered the case that L was a canonical bundle, and he proved that Higgs is holomorphically symplectic, and the map to the base is a Lagrangian map. In the neuromorphic case, you take L to be K with poles on some divisor D. So L is K series poles on D, which is an effective divisor. And I'm going to consider today only the case where D is reduced. So that's the tame case. Markman and Bottichin separately proved that the modulus which Higgs in that case is Poisson, and the map is Lagrangian or weakly Lagrangian, whatever you want to call it, meaning that the residue map from Higgs to the space of conjugacy classes at the points of D send the meromorphic Higgs bundle to the conjugacy class of its residue. So the symplectic leaves are just the fibers. So that means you have a map from your total space to some quotient object, so a quotient stack, and the fibers are the symplectic leaves in the Poisson. So the closure of the regular or generic symplectic leaves are parameterized by global sections of d mod W over the divisor D, and so there are fibers of the composition where you take the Hitchin map and follow it by the residue at the points of D. So these fibers are going to be the closures of the generic fibers. There are other fibers that are of lower dimension, which are kind of hidden and harder to visualize. And we will see some of those coming up in a little while. Okay. So my physicist friends are mostly interested in the simplest case, which is where you take the curve to be P1 with 4 branch points. So 4 is the smallest number where you have moduli. 3 of them will give you a rigid picture. So you have 4 punctures, 1 through 4, and lambda is a cross ratio, that's the modulus. In fact, you can construct an explicit global model for the whole family. Start with the plane, blow it up at 4 points, for example, the coordinate points 1, 0, 0, 0, 1, 0, and so on. And you can realize M04 bar is a family of conics through those 4 points. So you can just take this pencil of conics, pull it back to P2 tilde, blow up. Now you have a vibration. So you have a family, here it is, of conics C lambda. The generic one is just simply 1. There are 3 values of lambda, namely 0, 1, and infinity, where you get a reducible curve instead of a P1. So those are the 3 boundary points for M04 bar. And so at one of them you get a curve C0, which is given by, let's say, y tends to x equals 0. And then there will be a second one, 1, and then one at infinity. So the difference between those is just the distribution of which 2 of the 4 points set on which component of the curve. So this story turns out to be rich enough, so we'll just stick with that for now. So let's try to describe the Higgs field phi in terms of this model. So you can pick a global L which restricts to the right L on each of the curves. So on each of the curves you have 4 points. The canonical bundle would be O of -2. You allow poles at 4 points, you get O of +2. So the basic line bundle L is just O of 2. So you want a line bundle on the whole thing, which restricts to O of 2 on each of them, and restricts correctly to the singular phi. So you can write down this spectral curve by some equation where the phi k's are global sections relative to k that vanish to certain orders. So there's a matrix chi that describes the orders of the vanishing. It has 4 rows, I guess, corresponding to the 4 marked points. And n-1 is the rank of the algebra. So that's the number of invariant, the number of k's. So if all your nilpotents are regular, which is the generic case, then all the chi's are going to be 1, which is the smallest possible value. So making an nilpotent just says that it has to vanish, and making it a regular nilpotent says that it vanishes to the lowest possible order. Smaller nilpotent orbits are going to correspond to higher value of the chi's. And I'm going to show you some of these numbers in there. I think I'm saying it right here. So when the orbits of the 4 punctures are sufficiently big, for example, regular, we get a node that's unrestricted. We call such a node the standard node. In various cases, every node is a standard node. So those are not the ones we're going to look at. So a separating node, that means one that cuts the curve into 2 components. Yeah, so those are the nodes that arise in this example. So let's do the case where J is A3 or SL4. So consider the punctured sphere where each punctured residue of the X field is the regular one. So this is the easiest example. So that's the principal nilpotent orbiter of SL4. That's a mistake. That should be, it's not the principal, it's the regular. This corresponds required that all phi k have simple zeros. So that means that all the chi's were 1. So phi k is a section of L to the k, vanishing on the 4 exceptional divisors and nothing else. So this gives you a global section, a global description on the universal curve of what the phi's are. So you can compute with that quite easily. So here's a slightly larger than it needs to be picture of the two components. 2 of the marked points move to the left, 2 of them marked to the right. In this case, all of them say 4 to indicate that it's the regular nilpotent. Is there a problem? Okay. So the regular nilpotent for SLN are described by partitions of the number n. So let's say for SL4, is this visible?
Yes.
You can have the regular nilpotent, you can have a subregular, ... You can have the minimal nilpotent, and you can have the zero nilpotent. So the regular nilpotent corresponds to a single Jordan block of size 4. The subregular corresponds to a 3 and a 1. The minimal will correspond to a 2 and a 1 and a 1. And the 0 corresponds to 4 1-by-1 blocks. And in fact, I've only skipped one thing, which is 2 squared. One that doesn't have a good name. So you can describe this by a diagram either this way or this way. And similarly, this one would be this or this, and so on. So since there are 2 ways of doing it, and you can't decide which one you want, you give both the names. You call this one the Hitchin diagram, and this one the NAM diagram. So it's a fairly pointless distinction in the case of SLN. It becomes more important for the other groups, where the duality is actually, it's something called Spaltenstein duality, and it's actually fairly complicated. It's not 1-to-1, so you have to specify the NAM diagram and the Hitchin diagram. But fortunately, we don't have to worry about any of that. So in this particular case, the standard node, where we just have 4 in all of them, that means that my picture is something like 4, 4, 4, and 4, and I have a reducible curve containing them. Then I'm tabulating some of the information for you here. So here is explicitly the equation that's about cover. We've labeled all the coefficients. So if it says U2C, that means it's a quadratic differential, a section of L squared, that lives in the center. And L means left, and R means right. So what does that mean? If the equation is something like z times x minus y equals 0. So z equals 0 and x minus y equals 0 are the two components. So set one of them, let's say set z equal to 0. What's left will be a function of the right side of the curve. And conversely, you set the other coordinate to 0, you get something on the left. So things that vanish when you restrict them to the right, you label them by an L. Things that vanish on the left, you label them by R. If something doesn't vanish on either side, you call it central. And effectively, that means that it's supported at the node. Two-sided neighborhood of the node. So these numbers here give me the left, center, and right counts of how many parameters we have. So what does that mean? The group is SL4, so the degrees of the invariants are 2, 3, and 4. That's a quadratic differential, a cubic differential, and a quarter differential. So the first number, the first column gives me the numbers of quadratic differentials on the left, the center, and the right. And the second entry gives me the cubics, and the last one gives me the quartics.
Sorry, what am I supposed to learn from all this information?
Hold on 1 second.
Okay.
This is supposed to be the trivial example. I'm going to give you non-trivial examples, and hopefully they'll become clear. So this just repeats what I was saying about the base. So define the right and center part to be the stuff that vanishes on the left, and vice versa for the other side. So in this case, you get a plot. So the picture is, you have a large interval system that lives on the generic curve. If you count it, it has 21 base parameters. 12 of those are going to be Casimirs, meaning that they parameterize the symplectic leaves, and then the 9 remaining ones are the actual parameters on the base of a symplectic leaf, and then the curves will have genus 9, so you have a symplectic interval system. When you go to the node, the 9 is going to break into all these numbers. So roughly speaking, you have a 3, 3, and 3. You have a 3-dimensional interval system on the left. So you have a 3-parameter family of curves of genus 3 on the left. Another 3-dimensional interval system on the right. And in addition, there's 3 parameters in the center that tell you how to glue the curves on the right to the curves on the left. Okay.
So the goal is for each component of whatever dimension corresponding to the degeneration, we want to have an integrable system with a different gauge group, and they all together.
Exactly. So that's exactly the point. So we're going to learn how to calculate these groups, and then the reduced gauge groups that the physicists are baffled by are going to just arise in terms of calculating what happens to these Hitchin systems when you restrict them to the singular curve.
In that trivial example, what was the group on the node? I mean,
yeah. So in that case, the group is SL4, and yeah. So the orbit that I get is O4, and the group is SL4. So that's the standard node. It's the most generic picture. The orbit is regular, and the group H is the full group that you started with. There's no reduction. So if you do instead something like 3, 1, and 2, 1 squared, and 4, and 4. So I keep one side as before with the regular nilpotence, but I put some restrictions on the partition type on the other curve, on the other component. Then you go through the calculations, you get something like 0, 0, 0, 1, 1, 0, 0, 1, 2. 0, 1, 2 is what you get when you have the two regular nilpotents. So that's the same as what I had over there. This is the right, this is the left, this is the center. The fact that you have a bunch of zeros here, that's a telltale of an ugly theory. So in the ugly theories, you'll always have, well, you'll usually have no Hitchin system at all on one side or the other. So in this case, the node is still over 4, but this time you find that the group H is smaller. So the group, instead of being SU4, is reduced to SU3. Sorry, sometimes I call it SU and sometimes I call it SL. There's no logical distinction between them. Then you can do very similar examples, and in each of them you can figure out what's the node and what's the group in the node and what's the nilpotent at the node. Maybe the most entertaining elementary example, so I'll skip a few. This is my 5th example. I'm going to refer to it as such. So you do 2, 1 squared, 2, 1 squared, 4, and 4. So in this case, this is the first case where the nilpotent of the node cannot be regular. So in this case, it turns out to be the type 3, 1, and the group H is SU2. Actually, let me mention one last example. Let's go up to the next size group, SO5. So I'll do 3, 1 squared and 3, 1 squared and 5 and 5. And so now you have a system like that which has a certain number of center parameters. If you turn them off so that you get a nilpotent at the node, you get a system on the right which is 6-dimensional, and it's a Hitchin system on a single P1 with 3 nodes, 1, 2, and the action node, and a regular nilpotent at each of them. So that's boring. But on the left, you get a system that's 1-dimensional, so it's called the E6 Minahan-Nemeshansky integrable system. So it's a small system, but it cannot be realized. So there is no conjugacy class in SL5 such that this system is what you get on P1, from Hitchin on P1 with these 2 nodes in any third one. So from this point of view, it's completely mysterious. And it has secret E6 symmetry. In fact, if you move from if you use mirror symmetry to go to the Higgs branch, the Higgs branch ends up being the smallest nilpotent orbit of the group E6, the exceptional group. So E6, the Lie algebra E6 is actioned by conjugation. Okay. Let me, while I'm off my slide, let me mention one other feature that worth mentioning, which is the finer structure. So we have the moduli space with the Deligne-Mumford compactification of the moduli space. Over each point, we have a Hitchin system consisting of the base and some vibration over it. So the Hitchin bases form a vector bundle over MGN bar. What is it? So the only invariant that people have looked at is the rank of it. Well, it's a vector bundle. In fact, it's direct sum over I going from 1 to the rank of the group of subbundle BI, where BI is the section of the I2 power or whatever. But it turns out that there's a lot of finer information than just this obvious decomposition. And that comes from the global geometry of the moduli space. So for example, take G to be 0 and to be 4. So M bar is CP1. We know that every vector bundle on P1 decomposes as a direct sum of line bundles of certain degrees. So you have these hitherto unseen invariants, the degrees of the pieces in the base. So let me just write them down for you. So for example, so BI is going to have dimension 2i plus 1 because the basic line bundle is O of 2, the ith power is O of 2n, h naught is 2n plus 2i, so it's 2i plus 1. So what is that vector bundle? If I is even, let's say I is 2m, this ends up being 4 copies of O plus O of 1 up to O of m minus 1, and then 1 copy of O of m. And if I is odd, we get the same 4 copies of everything else plus 3 copies of O of m. So I don't know any conceptual way to see this. I just compute direct images under the map from P to tail dot to P1, and that's the decomposition I get. As far as I know, these are new invariants that have not appeared anywhere else. And the physicists are trying to figure out what they mean for the physics. How much of the time?
22 minutes. 22 or
22 minutes ago? Thank you. Okay. So this is a picture of example 5, I believe. So I've already explained that. So let's get that. Okay. So let me talk about some of the techniques that go into the analysis. So one part of it has to do with the local story. So forget the node, just work on the smooth curve and ask what's the relation between the nilpotent orbit and the singularity of the spectral cover. So a nilpotent orbit is specified by its Hitchin partition of the dual partition. The spectral curve has some equation where the AI are fluid differentials, a section of kc to the I was allowed pole of some order, or alternatively vanishing to some order, so the order of zeros plus the order of poles adds up to I. For a given nilpotent orbit OK, consider that the kth point, the 0 order is the row number containing I in the num diagram of OK. So let me just do that. So if I want to do the regular orbit, so So the NAM diagram looks like this. If I just label things, I get 1, 2, 3, 4. All of them are in the first row. So that tells you that all the chi's are 1. So that's how I got that all the chi's were 1 for the regular orbit. In the subregular, I'll have 1, 2, 3, and 4. So 3 of the chi's will be 1, and the 4th will be 2. So that means the quadratic and cubic differentials will vanish to first order, and the quartic differential will vanish quadratically. And similarly here, the NAM diagram will be this. So 1, 2, 3, 4. That says that the quadratic differential has vanished to first order, the cubic and the quartic vanish quadratically, and so on.
What is NAM diagram?
I'm sorry?
What is NAM diagram? It's just
The Hitchin diagram, or the Hitchin partition, I just take the Jordan blocks and make a partition.
pure algebra. What is special of NAM?
It's just a transpose.
So why it's called NAM?
Because for other groups, it actually has something to do with NAM's equation. And I'm not sure I can reconstruct it, but it somehow is related to NAM's equations. And there's neither NAM nor Hitchin determine the other in general. You need to specify both of them. So, like I said, it's something called spot and strength duality between orbits. All right. So so you do quick calculations like this, and you see that the regular you put an orbit has a single row, so it gives order dimension 1 for an I. The subregular gives a bunch of 1s and 2, and so on. The orbit only determines the generic form of the spell cover, not the actual form. So if you fix the orbit, that tells you what to expect for the spell cover, but you could have accidental further singularities. Or conversely, a given spell cover determines the smallest orbital. The actual orbit obtained from it may be anything containing it in its closure. So for example, the regular nilpotent corresponds to line bundles on C tilde. The smallest orbit corresponds to the direct image of line bundles on the normalization of C tilde. So there's a lemma somewhere that maybe due to Lamont that says that the Higgs field is regular if and only if the spectral sheaf is a line bundle. Generically, it will be a line bundle on a smooth curve, but it can also be a line bundle on a singular curve. But if it's not a line bundle, if it's a torsion free sheaf, necessarily on a singular curve, that will correspond to an irregular orbit. Okay. Coefficient AI is a section of the line bundle which you can write either in terms of the chi-i's or the pi-i's. We do some computations. You get that the space of all sections is vector space of some dimension bi. The space of all such sections. Yeah, so this is the formula in complete generality. This was when the genus was 0, which is the case we're interested in. So I mentioned the good, bad, and ugly. You say that the system is good if equality holds, which roughly corresponds to no high cohomology for the line bundles. Let's skip the statement. So you can also write down an explicit algorithm for describing the singularities of spell covers in terms of the resolution process. So the steps in the resolution are encoded in the Hitchin or NAM diagrams that control it. For that, I don't know how to do this in Firebase. So what we really want to do is consider Hitchin systems on singular curves and the generation from a smooth curve to a singular curve. So allow the curve C to be any Goldstein. Really all we need is just a stable curve with nodes. So any curve with nodes will do. As in the smooth case, the Hitchin system for the curve C reductive with G is a space of Higgs bundles of Kc valued Higgs fields. A G Higgs bundle is a pair of V phi, and so on. So all of this goes through pretty obviously. And again, you have a JT quotient or a static quotient. And you form the Hitchin base. The question is this a flat degeneration or is something jumping? So just a list of the results. The Higgs moduli space on the singular one, go inside curve, is going to be Poisson, as in Markman's results. Its symplectically are obtained by restricting the residues at each marked point to a coordinate orbit. The Hitchin map is weakly Lagrangian. So all of these are straightforward analogs of Markman's theorem in the smooth case. The weakness here is that I'm talking about actual Higgs bundles as opposed to Higgs sheaves. That means that the moduli space, the fibers of the moduli space are not going to be compact. So the system, while it has all the formal properties of the smooth case, it's not a proper system anymore. So you really want to figure out how to properize it, how to partially compactify it so it becomes proper, hopefully while remaining Poisson and keeping the leaves symplectic and so on. So as far as I know, that's not been done. There is a certain amount of work by these people on constructing compactifications, but they haven't checked whether the compactification is Poisson. So just the flavor of the result, we have results on the splitting of the base into left, center, and right pieces, which I tried to explain. We have some results about what happens as you go to the nodal limit in particular. Is it a flat limit? We have results about the singularities with flat covers, some stuff about the non-compactness of the fibers. In global structure of the bundle of Hitchin bases, that's what I was explaining over there. So if you consider just a one-parameter degeneration of family of curves CT degenerated to a singular curve C0, and the case of immediate interest is where we have a rational curve splitting into a left component and a right component, intersecting at the node P. So one thing you can show is that a sufficient condition for flatness is that the basic line bundle K, C0, and D on the singular curve is very ample on the limiting base curve. Then you can show that the Poisson and Hitchin system in the setting would form a flat would be a flat limit of the Hitchin systems for the varying curves. Particularly, the same holds for each of the symplectic leaves. So if the family of curves is the pencil of conics, our standard example, the condition simply says that there are at least 2 points on each component. Therefore, exactly 2 points on each component. So if two points go to each component, you're fine. If one goes to one and 3 go to the other, then it's not going to be a flat line. So the interesting feature then is that for our degenerating Hitchin systems, we see that the restriction to one component of the limit can be a proper subspace of the sections, let's say, on the right side. So this will happen on the right side when the line bundle on the left side has higher cohomology. And I'll show you the calculation in a second. In other words, when the degree Dij is less than or equal to -2, instead of just a line bundle P1. So, to make a long story short, you do some calculation, you see that you have numbers BI left, BI right, and BI center, let's say these primes. You calculate them, and they turn out to be things like the maximum, the degree on the left is 0, and so on. The prime indicates that this is the dimension that you get from the limit. On the other hand, the question is whether these dimensions equal their unprimed counterparts, which is what you get. And one of them arises in the limit as t goes to 0, the other one lives just on the limiting curve. And generalize a little bit, you look at the restriction sequence. The line of the singular curve goes in the line on the right. The kernel is the line on the right shifted by 1 with the branches of the node. So you just work out the long exact sequence and you get what I was trying to do. So back to this example number 5, which is the one there. So the order of poles is going to be 1 for the quadratic cubic and quarter differentials on the left, and 1, 2, 3 on the right. Those are the numbers that I have. Yeah, somewhere. So you do some calculations in smooth curves, you do some calculations in the limiting curves, and you get that the degree on the left is -2. So you know the occurrence of the -2. That tells you that this degeneration is going to be non-flat. That's essentially what leads to the group that you get in this case being SU3 as opposed to SU4. So this explains the reduction in the gauge group.
Is there kind of a more systematic way of saying that, like some invariant of non-flatness that you can read off that tells you why it's SL3?
I think it's sufficient but not necessary, but the condition is just that the degree of the line bundle, so that's going to be, for the ith line bundle, it will be 2 times I, let's say in the case of the derivative, it will be 2 times I minus chi I. And the chi i's are specified by the type of the dipole that you're importing. So if that number is -2 or less, that's when you're going to get a reduction.
Do you have a general formula for what the reduction is? Like if you started with gauge group SLN, then...
Yes. So we do it under some physics constraints, but the last section of the paper gives a complete classification of all the groups that you get. And it's actually a surprisingly small list. So when the upper gauge group is SUN, the only groups you can get are SUM for something less than n, or an orthogonal, or a symplectic, or E6, E7, and E8. And those are the only subgroups that you get. So it's an A, B, C, D, E classification. Anyway, let me just conclude. So a key puzzle for the physicists is that the Coulomb branches of the S-class theory is decomposed as hyperkähler quotients of products of Coulomb branches of limiting components. The group you need to divide by is often the full group, but sometimes the proper subgroup. That's the issue that I keep getting back to. So we give an algorithm for determining which is the case and what the weakly coupled gauge subgroup is. That's our realization due to BFN. So that's Nakajima, Finkelberg, and Braverman, going backwards, which counter to the intuition of my physicist friends, tells you that you can also get it as a hyperkähler quotient by the full group. So you can get the same Higgs space, the same Higgs branch as a hyperkähler quotient in 2 different ways. One is you follow the recipe here, dividing by H. And they have a different recipe where they start with a larger hyperkähler thing and divide it by the full J. And at the moment, it's very mysterious why the 2 quotients are the same. So you must. They don't think of it in terms of number of curves, but they end up getting the same order. So the point is that the nodal curve is just a crutch. The moduli of the theory is the same at all points. So you can calculate it at any boundary point. It's like the W, like the...
It's not just points, not just geometry. Some linearity in the structure from the way it generates the superconformal
I'm not sure. We've been talking with Nakajima about it, and he knows how to construct one way. way. Neither group knows how to reconcile the two constructions. It looks like they're both correct. There's two different hypercalic quotients which give you the same object at the end. Anyway, there's some recent progress on Higgs bundles and other curves, and what I mentioned some of these papers. For our purposes, it's important to understand not just the moduli spaces, but they did about system structure and that. And that's, as far as we know, this has not been done. Another direction in which the results could be applied is in the study of the character variety. This is related to the model space of Higgs bundles through another Deligne-Mumford correspondence. Unlike the geometry of Higgs bundles, the geometry of the character variety is completely independent of the choice of complex structure. Particularly, this means that you could choose to work with any complex structure of the curve and use the Deligne-Mumford correspondence to obtain the character variety. So another possible application is to the study of natural and blue coordinates of the character variety and behavior under different choices of Panzer compositions. So the key word there seems to be higher Fenchon-Nielsen coordinates. This is something that might happen someday. We have not really made any progress on that yet. So thank you very much.